Agarwal, Assistant Professor, JSS Academy of Technical Education, Noida. Today in this lecture, we are going to cover the topic disk scheduling. Now, when we talk about I/O management, then a very major term that we use is disk scheduling. Using disk scheduling, we can decide that how to perform the service the I/O requests that are coming. So, basically the operating system is responsible for using the hardware efficiently for the disk drives. This means having a fast access time and disk bandwidth. Now, before going deep into the access time and disk bandwidth, first of all let me quickly cover the disk structure, because without covering the disk structure it is not possible to cover the access time. So, this is the disk structure that we have. Here you can see we have an ARM assembly on which there are the read write heads. These are the read write heads. These are the disk platters on the surface of which this read write head rotates. All these platters or disks, they are rotating around this spindle. Okay. Now, all the disks are divided logically into different tracks. You can see here these blue circle, these are the tracks on which we have on all the disks, and every track is further logically divided into sectors. Here you can see this blue portion, that is the shaded one, this is a sector, right. So, this is basically the disk assembly where we have multiple disks that are attached on a spindle, on which the surface of which the read write head rotates to access the data on the disks. Now, the tracks that are on the same position of all the disks, they make a virtual cylinder, right. You can see here this dotted line, this is a virtual cylinder. So, we can, as many tracks we are having, will have the equal number of cylinders, right. If we have 200 tracks, we will have 200 virtual cylinders, right. The tracks at the same position, they will make a cylinder. Now let us come back to our disk scheduling, where we have our access time that is divided into two major components. First one is the seek time and the second is the rotational latency. Now, seek time is what? Seek time is basically the time required for the read write head to bring to the desired cylinder, right. So, to move the head to a particular cylinder, the time that it takes, it is called seek time, and seek time obviously it is directly proportional to seek distance, okay. And we will always like to minimize the seek time, because this is just an overhead. We would always like to minimize the head movement, okay. So, our aim is to minimize the seek time. Now, once the track is brought under the head, then the sector needs to be bring under the head. So, that time the time that is required to bring the desired sector under the head is called rotational latency, okay. So, seek time is what? Seek time is the time required for the head to bring under the desired track, and to bring the head under the desired sector is the rotational latency, okay. Now, then comes a term that is called as disk bandwidth. What is disk bandwidth? It is the total number of bytes transferred divided by the total time between the first request for service and the completion of the last transfer. So, whatever total time is required between the first and the last request, if we divide the total number of bytes by that particular time, we get the disk bandwidth. Now, for disk scheduling, we have several algorithms. Now, before starting the algorithms, let me tell you, this is the request queue that we are going to follow for all the algorithms in our lecture. Now, what is this request queue? The request queue, you can see here number 0 to 199. What is this? This is nothing but these are 200 cylinders. Okay. We have 200 cylinders ranging from 0 to 199, and this is the request queue that is given to us, the sequence in which the request has come, and this is the current head position. That means, obviously at a particular time the head must be resting somewhere. Okay. So, we are assuming that the head is currently located at location 53. Okay. So, in all the algorithms we will take this particular case where the head is at 53 and this is the request queue. Now, moving to the our first algorithm, that is first come first serve. Now, first come first serve, the name itself tells that whichever request comes first, that will be serviced first. Okay. So, here you can see this is the same queue that we did in the last slide and the head is at 53. Okay. So, to start with, this is the current head location 53. The first request is of cylinder 98. So, the head will move from 53 to 98. Okay. So, while moving from 53 to 98, what is the total head movement? 98 minus 53, that is 45. So, we have a total of 45 head movement for moving from 53 to 98. Now, after 98, the next request is 183. So, from here 98, the head moves to 183. Now, what is the head movement? 183 minus 98, that means 85. We have a total head movement of 85 for moving the head from 98 to 183. Then from 183 the next request is 37. So, from 183 the head will go to 37. Now, what is the head movement? From 183 to 37. So, it gives us 6 and 14. That means 146 is the head movement from 183 to 37. After 37, next request is 122. So, from 37 the head moves to 122. Now, here what is the head movement? 122 minus the head moved from 37. So, we have 85. 85 is the head movement for moving the head from 37 to 122. From 122 the next request is 14. So, here from 122 it goes to 14. Now, what is the head movement? 122 minus 14, it gives us 108. So, 108 is the head movement from 122 to 14. Now, from 14 the next head movement is 124. So, from 14 it will come to 124. Now, what is the head moment? 124 minus 14. So, it gives us a total head moment of 110 cylinders. Now, from 124 next request is 65. So, from 124 it will go to 65. So, now what is the head moment? 124 minus 65. So, it will give us 59 cylinder movement. Then finally, the last request is of 67. So, from 65 it moves to 67. So, what is the head movement now? 67 minus 65, that is 2, right. So, these are the head movements that we have calculated. Now, we have what we need to calculate? The total head movement. Total head movement will be calculated by just summing up or adding all the head movements that we have calculated individually. That means adding the values, the first movement, the second movement, the third movement, fourth movement, fifth movement, sixth movement, seventh movement and eighth movement. If we add all these head movements, we will get the total value, and here in this case it is coming up to be 640 cylinders, right. So, this is how we calculate the head movement in this first come first serve scheduling algorithm. Okay. Now, let us moving to the next scheduling algorithm, that is SSTF. SSTF is an abbreviation for shortest seek time first. Now, shortest seek time first, it is the name itself tells that here we are talking about the shortest seek time, right. So, means the request that is nearest to the head, that will be serviced first. If we go in our flashback, then in CPU scheduling we have our SJF scheduling, that is shortest job first scheduling, where the process with the smallest burst time used to be processed first. So, this is almost similar to that one, where the request that has the shortest seek time, that will be serviced first. Now, here you can see we have the same queue, the head is again at 53, right. Now, here let us say what will be the sequence of servicing the requests. Now, the head is at 53, right. Now, in all these requests, which request is closest to 53? The closest one is 65. So, this request will be serviced first, and it will give us a head movement of 65 minus 53. So, it will give us 12, a movement of 12 cylinders. Now the head is at 65. Now, from the remaining ones, which cylinder is nearest to 65? 67, right. So, the next request that will be serviced is 67, and that will give a head movement of 67 minus 65, that is 2, only 2 cylinders, right. Now, the head currently is now at 67. Now, which cylinder is closest to 67? If we see, the closest one is 37, right, that gives us the minimum head movement. So, it will give us a head movement of from 67 we are going to 37. So, 67 minus 37, that means 40. It will give us a head movement of only 40 cylinders. Now, from 37, which is the nearest one? The nearest one is 14, that will give us the minimum head movement. So, the next request that we are servicing is of 14. So, now what is the head movement here? That is your 37 minus 14. So, this will give a head movement of 23 cylinders. Now, from 14, the head is now at 14. From 14, which is the nearest cylinder? The nearest cylinder is 98. Okay. So, head will now move from 14 to 98. It will give us a head movement of 98 minus 14, that means 84 cylinders. Okay. Then from 98, which is closest? The closest is 122, which will give a head movement of 122 minus, the head was at 98. It will give us a head movement of 24 cylinders, right. Now, closest to 122 is 124. We have covered 122 is covered and our 98 is also covered. So, 124. Now, from 122 to 124, we will get a head movement of 2 cylinders from 122 to 124, right. And finally, the head will move from 124 to 183, which will give us a head movement of 183 minus 124. That will give us a head movement of 59 cylinders. Now, if we sum up all the head movements, 1, 2, 3, 4, 5, 6, 7 and 8. If we sum up all the head movements, we will get a total of 236 cylinders, which is very less as compared to first come first serve. In first come first serve, it was 640, and here you can see it is just 236, a remarkable difference, right. So, just like SJF in CP scheduling, SSTF is also the algorithm that gives us optimal results. Okay. Now, then comes our next algorithm, scan. Now, what is scan? Scan is basically an algorithm where the head moves in one direction till the extreme end and it services the request that comes in between. Okay. So, the disk arm starts at one end of the disk and moves towards the other end, servicing the requests until it gets to the other end of the disk, where the head movement is reversed and servicing continues. Now, before explaining this algorithm, let us take an example of an elevator or a lift, you can say. So, what happens? Suppose you are standing on a particular floor, let us say on your 10th floor, you press the button there and the lift is currently at ground floor. So, while coming up to 10th floor, if there is any other button pressed in the intermediate floors, then the lift will stop at all those floors, right. That means it is servicing all the requests that are coming in between. So, the same principle here is with your scan algorithm, right. So, here the head moves in one direction, servicing all the requests that comes in between. Now, here if we see that and therefore, this algorithm is also called as elevator algorithm, right, because the principle is same, fine. So, now here we say that currently the head is at 53. Okay. Now, from 53 we are assuming the head is moving in this particular direction. So, while going to this direction, whichever request comes, it will service those requests. So, which requests are coming on the way? First of all, it will service request number 37, then it will service the request number 14, and then it will reach the end of the disk, that is 0, right. Now, when it reaches 0, it reverses its direction and then it starts moving in this direction, servicing all the requests that comes in between. So, the first request that comes in between here is request for cylinder 65, then it services the cylinder request of 67, then request of 98, then 122, then 124, and finally, it will go to 183, right. So, this is the principle of scan algorithm, where the head moves in one direction, services all the requests that comes on the way, and after reaching the end of the disk, it reverses the direction and it services all the requests that come on the return path, right. So, the calculation of the head movement is same as it was there in the FCFS and SSTF. Like first of all, we will calculate from 53 move to 37. So, 53 minus 37 will calculate, then 37 to 14 will calculate, 37 minus 14, then from 14 will go to 0. So, this is also calculated. So, 14 minus 0. Okay. Then from 0 it came to 65. So, the next movement will be 65 minus 0. Then 67 to 65, 67 minus 65. Then from 67 it moved to 98. So, 98 minus 67, from 98 to 122. So, 122 minus 98, from 122 it moved to 124. So, 124 minus 122, and finally, from 124 to 183. So, 183 minus 124. Just by summing up all the head movements, calculating this way, we will get the total head movement of 208 cylinders here, right. So, this is your scan algorithm, in which the head moves in one direction and services the requests that come on the way. Another name of this is elevator algorithm. Another version of scan is circular scan, or in short we also call it as C scan. Okay. So, here what we have? Here it behaves like a circular list, like when the head reaches one end of the disk, it does not reverses the direction, it will go to the start of the disk, right. For example, if the head goes to 199, from there it will directly go to 0, right, just like a circular linked list. It behaves like a circle, like here it is ending, from here it will start again. Okay. So, the head moves from one end of the disk to the other, servicing the request as it goes. When it reaches the other end, however, it immediately returns to the beginning of the disk without servicing any request on the return trip, right. That means, the direction of servicing the request will always be the same. and it also provides a more uniform time than scan. So, it treats the cylinder as a circular list, like here you can see. Here let us say the head is moving in this direction, right. So, it covers all the requests that come on the way. From 53 it covers 65, then it covers 67, then it covers 98, then it covers 122, then it covers 124, then 183, and finally it reaches at the end of the disk, right. Now, while going back, it is not servicing any request. From 199 it goes to 0 directly, and then starts the servicing the request in the same direction. First of all it services 14, then it services 37, right. This is how circular scan works. The calculation of head movements remains same in all the algorithms. Now, next algorithm is look. Look is a version of scan algorithm, of our elevator algorithm. The only difference between scan and look is that in scan algorithm the head goes till the extreme end of the disk. That means it goes to 0 and other side goes to 199, right. But in look it goes till the last request, it does not go till the extreme end of the disk, right. If the request is ending at 14, it will come back from 14, it will not go till 0, right. This is our look algorithm where it goes only till the last request. And the last algorithm is our C look, that is a version of C scan. Just like look is a version of scan, C look is a version of C scan, circular scan, or you can say here circular look. Now, here you can see like the head is moving in this direction. From 53 it services all the requests that comes in between. The last request here is of 183, right. From 183 it moved to 14, whereas in circular scan it went till 199, and from 199 it went here for 0, then it reverses back. But in look it saves a lot of head movement by just going till the last request, okay. And from there it goes to, from 183 the request here is 14, so it will not go at 0, and here it will not go till 199, right. So, this particular head movement is saved in case of C look or circular look, right. So, these are all the disk scheduling algorithms that we have. Now, finally, selecting a disk scheduling algorithm. Now, as I have already told while discussing SSTF, that SSTF has a common appeal, it has a natural appeal because it gives us the minimum head movement or the most optimum head movement in most of the cases. But in every case obviously no algorithm can give the best performance in every case, because there are a lot of constraints, right. Like scan and C scan perform better for systems that place a heavy load on the disk, because they are less likely to cause starvation, right. Then performance also depends on the number and types of requests. Along with the types of requests, a lot is dependent on the file allocation method also. For example, if we have contiguous allocation, contiguous allocation means that we have all the requests that are nearby, right. So, there will be less head movement. If we, on the other side, if we have linked allocation or indexed allocation, that means the requests are scattered all over the disk, right. So, obviously, it will lead to a much more head movement. So, because of all these complexities, the disk scheduling algorithm may be written as a separate module if required, because it has lot of things that needs to be considered. So, to summarize it, either SSTF or look is a reasonable choice for the default algorithm. So, if you compare the results from of the example that we have done, you will see that shortest seek time first and look algorithm are giving us quite good results. The results are quite impressive if we are using SSTF or look, right. So, this is all about disk scheduling. That is all for now. Thank you.